Hello. Hello, how's everyone doing? Sorry that I scheduled it in the AM instead of the PM, and I didn't even notice. I hope no one was actually, like, waiting, because that would be very early in the morning or, like, late at night for, I think, the majority of my viewers. I'm so sorry. But yeah, just, if you see anything that's in the or in the AM, it's probably not. It's probably a mistake on my part. I'm so sorry. But hopefully it's fine, right? Anyways. Today we'll be learning about vectors, so get your notes ready. I found my calculator from last time. I was like trying to find it last time, but I found it. And it still works. It's super old. And it's like all the paint is faded off the buttons. But I found it. Or you could use your phone. Or you don't have to use your calculator if you don't want to. I structure my sleep schedule around your screams and nothing else. How could you? I'm, you know, yeah, my bad. but so yes, I guess for future reference, in case that happens, if you see something that is like in the AM, it's probably because I accidentally mixed it up, and this has happened to me before. I do have like a schedule posted on. Speaking of which, I need to post on Blue Sky. On my Blue Sky, as well as my Twitter community, or not my Twitter community page, my YouTube community page, and I have like a scheduled thing for YouTube where I just post the picture as the thumbnail. So there's that. If there's any question as to why I'm streaming at like 3 AM, it's probably because I did it wrong, and it was supposed to be 3 PM. I don't even have a schedule, so I'm in no position to give you a hard time. Okay, but I'll stop yapping, and we shall get to the actual learning, and I will play some background music. The thing about this is because I'm using like a copyright-free playlist on YouTube, unfortunately it will stop occasionally. So that will be that, and of course you cannot hear it right now. Now you can, right? Not too loud, not too quiet. Let's go! Yes. So today I hope to go over the concept of scalars and vectors, as well as the coordinate systems and components of a vector. If we have enough time, I will go over the algebra of vectors. If not, we'll go over that the next time I do like a physics learn with me stream. I think I have the book listed in the description, and it is completely free. If not, I should pin it. Hold on. Give me a moment. Let me pin it to the chat, and I will check the description afterwards. But feel free to, like, read along with me. I am not a great reader, so there's that. But yeah, this book is free and open sourced. And we are in chapter 2, so. Let me pin it. I really am not prepared today. My brain muscle apparently not working too well. Pin the chat and pin this as well to the Twitch side. Manually pin, yes. It's pinned, right? Okay, I hope that pin does not go away, but we'll see. It's okay, you gotta get warmed up. I did eat lunch. You know, I kind of just woke up, ate lunch and breakfast. I ate brunch and then did nothing. Let's set this up and then continue. I washed the dishes. That's what I did today. Alright. So, chapter 2 in vectors. So here's the introduction. Figure 2.1. A signpost gives information about distances and directions to the towns or to other locations relative to the location of the signpost. Distance is a scalar quantity. Knowing the distance alone is not enough to get the town. We must know the direction from the signpost to the town. The direction together with the distance is a vector quantity commonly called the displacement vector. A signpost therefore gives information about displacement vectors from the signpost to the towns. So if you notice from this, it's giving us two pieces of information. And I think that is like the most important part about learning about vectors, is that it gives you two pieces of information. But it'll tell us the difference between a scalar and vector, and that's when we'll really get into it. Introduction. Vectors are essential to physics and engineering. Many fundamental physical quantities are vectors, including displacement, velocity, force, electric, and magnetic vector fields. Scalar products of vectors define other fundamental scalar physical quantities, such as energy. Vector products of vectors define still other fundamental vector physical quantities. They look the same, such as torque and angular momentum. Qualities. No, there's no L. Quantities. There's no L. Quantities. In other words, vectors are a component part of physics in the same way as sentences are a component part of literature. In introductory physics, vectors are Euclidean? I think that's how you say that. Quantities that have geometric representations as arrows in 1 dimension in a line and 2 dimension in a plane, or 3 dimensions in a space. They can be added, subtracted, or multiplied. In this chapter, we explore elements of vector algebra for applications in mechanics, in electricity, and magnetism. Vector operations also have numerous generalizations in other branches of physics. Alright, so from this little small introduction, we can get that. Put like intro. From this small introduction, we can see that these are physical quantities. So they describe physical quantities. Describe physical quantities. And hello, hi. I just saw your message, sorry. I was so absorbed in reading. Scalar products of vectors also define. So scalar products of vectors define other fundamental quantities. Why is that so hard for me to say? I don't know. So maybe you'll write that down too. That seems important. Of vectors. Define. Why is my writing looking like that now? Define scalar qualities. So I guess scalars have their own sort of quality in a way. Scalar physical. So there's a difference between scalar physical quantities and scalar physical vector physical quantities. TES, okay. And then they have geometric representations as arrows, or plane, or in a space. So we'll put representation. Representation, and then we'll have like 1D is a line. We'll have 2D as a plane. And 3D as a space. That looks like a P. There we go. Space. And then you can do operations on it. But yeah, now we can get into the fun part and actually learn about like what they truly mean and then how to sort of manipulate them to represent certain things. So do section 2.1, scalar and vectors. Learning objectives. By the end of this section, you will be able to describe the difference between vector and scalar quantities, identify the magnitude and direction of a vector, explain the effect of multiplying a vector quantity by a scalar, describe, I swear I'm not doing this on purpose, describe how one-dimensional vector quantities are added or subtracted, explain the geometric construction for the addition or subtraction of vectors in a plane, distinguish a vector equation or a scalar equation. So, many familiar physical quantities can be specified completely by giving a single number and the appropriate unit. For example, a class period lasts 50 minutes, or the gas tank in my car holds 25 liters, or the distance between two posts is 100 meters. A physical quantity that can be specified completely in this manner is called a scalar quantity. Scalar is a synonym of number. Time, mass, distance, length, temperature, and energy are examples of scalar quantities. So that seems important. This defines what scalar means. So we'll have definition. Scalars means it can be described by a single number and a unit. So, a physical quantity that can be described by a single unit. Physical quantity. Quantity. Did I spell that right? Yes. That can be described by a single number. Why does that D look like that? Described by a single number and unit. Or I should say with unit. Yeah. Okay. So there'll be that, and then here are some examples. So for example, like time, you can just have it in seconds. It doesn't have like two components to it. Scalar quantities have the same physical units. Scalar quantities that have the same physical units can be added or subtracted according to the usual rules of algebra for numbers. For example, a class ending 10 minutes earlier than 5 minutes lasts 50 minutes minus 10, so 40 minutes. Similarly, a 60-calorie serving of corn followed by a 200-calorie serving of donuts, now I want to eat donuts, gives us 60 calories plus 200, which is 260 calories of energy. When we multiply a scalar quantity, when we multiply a scalar quantity by a number, we obtain the same scalar quantity, but with a larger or smaller value. For example, if yesterday's breakfast had 200 calories of energy, and today's breakfast has 4 times as much energy as it had yesterday. Then today's breakfast has 4 times 200 calories, so 800 calories of energy. Two scalar quantities can also be multiplied or divided by each other to form a derived scalar quantity. For example, if a train covers a distance of 100 kilometers in 1 hour, its speed is 100 kilometers divided by 1 hour, so you can get the meters per second, where the speed is a derived scalar quantity obtained by dividing distance and time. So you can basically just do regular arithmetic on scalars, and I think this part is a standout where you take two scalar quantities, you can divide them to form a scalar or a derived scalar quantity. So we say you can add, subtract, and multiply / divide. I'll put that like right here. Maybe I will pull these notes a bit more this way. I just learned vectors around a month ago for my physics class. I will use this as review. Yes. Review is always good. Very helpful. I hope that this review is helpful to you, though. I'm not the best at teaching. I kind of sort of just started learning how to actually do a method like this, or stream format like this. So you can add and subtract. That's in R. Subtract, multiply, and divide. Divide. So this will work on the same unit of, how do I say this? You can do all of this simply if they have, well, you can technically do it from units with scalar quantities that don't have the same units. I should just say be mindful of units then, maybe. But be mindful of units when you do this. Yeah, and then another thing is you can get a derived scalar quantity from two different scalar quantities with different units. For example, that like speed. Can derive scalar quantities, and then this can come from two scalar, I'm gonna call them scalar values if that's okay. So basically, instead of calling them scalar quantities, I'm gonna call them scalar values because it's a bit shorter. Two scalar values. It'll help me write the notes better, I think. And quantities is for some reason really difficult for me to say. Two scalar values. Then you can get from two scalar values, you can get another scalar quantity. How do I explain this? So you can derive scalar quantities from two scalar values. Yeah, I think that will make sense, right? And then maybe I should put an example. I feel like the example really helps. So we'll just put the same one that they did. So we'll have like 100 kilometers and 1 hour as our two scalar values. And then you can just divide the two. km divided by 1 hour, and then you get 27.8. That. And that is our scalar value, or derived scalar value, or scalar quantity. I just don't want to study integrals. I'll watch this to procrastinate on math while still being productive. I don't know. So this textbook might actually, we might actually use integrals eventually. I haven't gone far enough to look into it, but hey, maybe study your integrals because you'll probably need it later anyways. Many physical quantities, however, cannot be described completely by just a single number of physical units. For example, the US Coast Guard dispatches a ship or a helicopter for a rescue mission. The rescue team must know not only the distance to the distress signal, but also the direction from which the signal is coming, so they can get its origin as quickly as possible. Physical quantities specified completely by giving a number of units, magnitude, and a direction are also called vector quantities. Examples of vector quantities include displacement, velocity, position, force, and torque. In the language of mathematics, physical vector quantities are represented by mathematical objects called vectors. We can add or subtract two vectors, and we can multiply a vector by a scalar or by another vector. We cannot divide by a vector. The operation of division by a vector is not defined. So, go back here and we'll write vector. Can I recommend a clicker game you might like to make a video on? I actually have like too many games I need to make streams on, or need to play. Recently, like, I guess it's not super, well, sort of recently. Recently, someone like bought out my wish list of games, and I was like, oh my gosh, thanks. But I really want to get to those first before I start playing any other games. But we'll write what vectors are. Vectors, so they are okay, vector quantities and just vectors. But I always thought vectors was this. But okay, we'll write vector quantities as the definition instead of just vectors, the way that I did with scalars. Vector quantities. So these are described by a number of units, a magnitude, and a direction. This reminds me of that like Despicable Me quote with the evil the person in like the orange tracksuit. I'm gonna go see you. All right, thank you for stopping by. I appreciate it. So, units, or I should say number of units. Good afternoon. Hello, good afternoon. Vector. Yeah, his name is literally Vector, right? But he always used to say something. He's like, he had this quote. It was something like of magnitude and direction. I forgot it. Direction, number of units, and So it has like two values in a way. I'm gonna put another thing. It says like has two components. I maybe shouldn't say values, components. I think I spelled that right. Hopefully I spelled that right. And then we can say physical vector quantities are described, and they're just described by something called vectors. Okay. It's two components described by vectors. Who would have thought vector quantities are described by vectors? Described by vectors. And then you can add, subtract, but you cannot divide. So that's the important part. Add, subtract. And multiply. No division. I'm gonna put no dividing. No dividing. The operation of division by a vector is not defined. So, they give us a little cute example with a very cute dog. From the tail of a vector origin to the head of a vector end. That's the vector. Oh, I see. So they're explaining that like it can be described as arrows. We draw a vector from the initial point, called the origin, or the tail of a vector, to the end, or the terminal point, called the head of a vector, marked by an arrowhead. Magnitude is the length, and is always positive. Is always a positive scalar quantity. So that's important to know. So we can describe it with an arrow, the tail, and a head, and then maybe I'll just draw it. So we'll have this as like the origin, or maybe I should pick a different color for that. I'll pick black for the tail, so that's like an example. We have that. I cannot draw a straight line, but that's supposed to be a straight line. And I'll draw arrows, or like lines pointing, so it's like tail, then head, and then this length is the magnitude, which is always positive. So this magnitude relates to this magnitude up here. I don't know if you can see my pointer too well. But right here, this magnitude, the number of units, and then a direction, this magnitude is that. So this basically tells you the value, and then where it's pointing tells you the direction. And then put always positive. Always plus. Yeah, okay. Hold on, I kind of want to find that. I keep thinking about it. That Despicable Me character in that quote. I kind of want to find it. Maybe I'll add it into the summary at the end. Because it does actually explain the fact that it has two components. Despicable Me. And then it's gotta be a quote. Oh, wait, okay, yeah. So here's the quote. Vector, that's me, because I commit crimes in both direction and magnitude. So yes, there's direction and magnitude. And maybe for this one, I will put arrow points in direction. Points in direction. let's examine vector algebra using a graphical method to become aware of the basic terms and to develop qualitative, this time it's qualitative, understanding. In practice, however, when it comes to solving physics problems, we use analytical methods, which we will see in the next section. Analytical methods are more simple, computational, and more accurate than graphical methods. From now on, to distinguish between a vector and a scalar quantity, we adopt the common convention that a letter in bold type with an arrow above it denotes a vector, and a letter without an arrow denotes a scalar. For example, a distance of 200 kilometers, which is a scalar quantity, is denoted by d equals 2 kilometers, whereas displacement of 2 kilometers in some direction has a vector quantity denoted by, and then you have the bold d with the arrow on top. So this is going to be hard for me to write, I guess, because I can't really make things bold. Like, I can line it, but for the sake of me writing it, I will write it with an arrow on top. I could do like this and just go over it a few times, but I don't think there would be that much of a difference. But I guess for my personal notes, please note that if there's an arrow on top, that means I'm relating to a vector quantity or vector value. Suppose you tell a friend on a camping trip that you've discovered a terrific fishing hole 6 kilometers from your tent. It is unlikely your friend will be able to find the hole easily because you also communicate the direction which it can be found with respect to your campsite. You may say, for example, walking about 6 kilometers northeast from my tent. The key concept here is that you have to give not only one, but 2 pieces of information. Yeah, the 2 components, 2 pieces of information. Namely, the distance, or magnitude, and the direction, northeast. Displacement is a general term used to describe a change in position, such as during a trip from the tent to the fishing hole. Displacement is an example of a vector quantity. If you walk from the tent, location A, let's bring up the figure so you can see. You walk from the tent, location A, to the hole, location B, which right there. The vector D represents your displacement, as drawn as the arrow that originates at point A and ends at point B. The arrowhead marks the end of a vector. The direction of the displacement vector D is the direction of the arrow. So basically, this length shows magnitude, and then the direction of the arrow shows the direction. The length of the arrow represents the magnitude D of vector D, where D is equal to 6 kilometers. Since the magnitude of a vector is its length, which is a positive number, the magnitude is also indicated by placing the absolute value notation around the symbol that denotes the vector, so we can equivalently write that D, not the vector D, is equal to the absolute value of the vector D. To solve a vector problem directly graphically, we need to draw the vector D to scale. For example, if we assume 1 unit of distance, 1 kilometer, is represented in the drawings by a line segment of a length u is equal to 2 centimeters, then the total displacement in this example is represented by a vector of the length d is equal to 6u, and then we have u is equal to 2 centimeters, so it's 12 centimeters, shown in figure 2.3. Okay, notice here, to avoid confusion, we use d is equal to 6 kilometers to denote the magnitude of the displacement, and little d is equal to 12 centimeters to denote the length of its representation in the drawing. So let's go to this. The displacement is 6 kilometers, and the length. I'm a bit confused by that example. Okay, so they're using like 1 centimeter to say that it's 1 kilometer. Like a scale, I guess. I think. Yeah, I think. Okay. The displacement of d of magnitude 6 kilometers is drawn to scale as a vector. Oh, wait, hold on. No, never mind. To scale as a vector of length 12 centimeters, where the length 2 represents 1 unit of displacement. Okay, so let's try to break that entire section down before we move on. I'll have it like this. Maybe I should zoom out a little. I keep always going more and more diagonal. Let's try to re-correct that so I don't go more and more diagonal. So here, we like right here. So we can use a vector quantity denoted by that example. I'm 35 minutes late to class. It's fine. I've been later, and I'm happy you showed up though. You're late. How dare you? Vector denoted by, or yeah, we'll just put small. Noted by, and then I might also write them in different colors. I think when I do refer to a vector, instead of like bolding it, I'm gonna choose a different color. Red feels like it's too bright. Orange is also way too bright. Purple is too close, but maybe there's like lighter purple. So when I refer to vectors, as in like when I write it out, instead of bolding it, I'll write it in purple. I still will write the arrow on top though, so. And then we can put a scalar. A scalar is denoted like this. Scalar denoted, and now just put like a lowercase d. Like that. Yeah, okay. Hopefully that people can see the difference and they'll understand. Does this make sense? Is everything I'm like writing down making sense to you, or partially making sense to you? I hope so. So, like you said, it has 2 pieces of information. And then we go into displacement. So they chose displacement to describe what a vector is. I think I'm going to make this one a bit further out, actually, since it's sort of like its own example. Displacement example. It represents a change in position. Speaking of which, when sometimes I get lost track of where I am on the sheet and my head will block the notes. Please tell me if I'm blocking the notes with my head. I will either move myself or move the notes up. Okay, so displacement is a vector quantity. Vector D representing our displacement. It's an arrow with an A and B point, so that is like the tail and the head we just wrote earlier. The arrow marks the end of a vector. We got the tail, the direction of displacement vector. is the direction of the arrow. So that is all explained here, right? So hopefully this just should be enough to explain it, but just note that the magnitude is length and the direction of the arrow is where it's pointing to. The length of the arrow shows magnitude of d, yes, okay, where it's 6 kilometers, and since the magnitude of a vector is its length, which is a positive number, the magnitude is also indicated. So if I take the absolute value of a vector, you get the magnitude. Hello teacher, how are you doing today? I'm doing good. How are you? So we'll write the absolute value of a vector is the magnitude. I think that would be important for knowing what is what, or like what you can do a vector to get the information you want. The absolute value of vector is magnitude. There we go. And to solve a vector problem graphically, we need to draw the vector d to scale. Oh, I see what they're doing. So they are basically putting a ruler against this thing and figuring out the displacement. So if we assume 1 unit of distance as 1 kilometer is represented in the drawing by drawing a line segment of 2 centimeters, the total displacement. Where does the 6 come from? Oh wait, it's 6 kilometers of. Oh, the magnitude is 6. Right? Yes, the magnitude is 6. Okay, so that's where it's from. So they're drawing a line to represent that. And the length of that is 2 centimeters. So this length of this line that they're using to represent the 6 kilometers is 2 centimeters. Then the total displacement in this example is represented by the vector length. So the entire length of that is 12 centimeters. Notice here, to avoid confusion, we use d is equal to 6 kilometers to denote the magnitude of the actual displacement, and lowercase d, 12, to denote the length of its representation in drawing. Oh, so they're using this ruler to essentially try to represent this in like drawing and making a graph. I get it. That makes sense. Hello again, Barry. Hello. Suppose your friend walks from the campus campsite at A to the fishing pond B, then walks back from the fishing pond to B. From the fishing pond at B to the campsite A. The magnitude of displacement vector is this. From A to B is the same as the magnitude of displacement vector dBA. From B to A, it equals 6 kilometers in both cases. So we write DAB is equal to DBA. However, vector DAB is not equal to vector dBA, because the two vectors have different directions. So here they're saying that because the length is the same, aka the magnitudes are equal to each other. However, the entire vectors are not the same because they're pointing in different directions. In figure 2.3, so this campsite one, vector dBA would be represented by a vector with an origin at point B and an endpoint at A, indicating vector dBA points to the southwest, which is exactly 180 opposite to the direction vector DAB. We say that the vector dBA is anti-parallel to vector DAB, and write DAB is equal to negative DBA, where the minus sign indicates anti-parallel direction. The two vectors have identical directions, are said to be parallel vectors, meaning they are parallel to each other. The two parallel vectors, A and B, are equal, denoted by A equal to B. If and only if they have the same equal magnitudes. Okay, two vectors with a directions perpendicular to each are said to be orthogonal vectors. These relations between the vectors are illustrated down below. Okay, so here is the types or labelings of the vectors. Okay, so let's start from this part so we can learn how to label things. So to label a vector, label a displacement vector. And my music stopped. Lovely. Displace. Label a displacement vector. That would be labeled by the points. So we'll put 0.1. I'll put like, or I should say origin point. Origin? ORGIN. Origin. How do you spell origin? The more I do these, the more I realize, wow, I really can't spell anything. Origin point to end. And then you'll have the magnitude. Oops. I should say the variable representing that magnitude. Or that, like, is it called variable? Variable representing representing that magnitude. Okay, there we go. And then that would look like, change it to the color purple, because this is now a vector. Like this. And we'll put origin, just have it like A and B. So that's how you label it. And then if they have equal magnitudes, okay. How do I write this down as notes? I need to think. I want to write it down, but I feel like the book just does it so much better. And I wanted to turn on my music as well. So if they have the same magnitude, that doesn't necessarily mean they have the same direction / same vector. Maybe I'll write it like that. So we'll write can have same magnitude and have same magnitude, but different, and I'll call it different vectors. can have same magnitude but has a different vector. What else? Yes. It can have different vector. I shouldn't say different vector, because it can technically have the same vector. Can have same or different vector if it has the same magnitude. As same magnitude. So basically, if you want them to be equal to each other, they have to be equal exactly. They have to have the same magnitude and the same direction. We can say that something's anti-parallel if their magnitude is the same but in the opposite direction. Okay, now is where I'm gonna write it down just like the book does. So we'll call it anti-parallel. Anti-parallel. Which means this. That's a B. I need the arrow on top of that too. It's like that. Okay. Identical directions. Two vectors that have identical directions are parallel. So, same direction. Then how would I write that like this? I feel like I just want to screenshot this and then put it in here. Maybe I can. Hold on, let me try that. Also, I think my voice does need a little bit of a break soon. But give me a moment. I'm gonna try to screenshot that. In the meantime, let's take a small little break. But how are all of you doing? I hope you're doing well. You're studying. Can I copy this? I can put it in there. I'm gonna take some water. I'm gonna have a little short water break. Make sure to stay hydrated too, and to stretch, or else you'll get a bunch of back problems. I'm already too late on some of that, but it is what it is. Okay. This is work. Yes. I was just refilling my water. Yes, refill your water. I wonder how much more do we have in this section. This section is super long, which is why I was only thinking maybe we could only do 2. Let me look ahead. Oh my gosh. Maybe we can only do 1, unfortunately. The section's a lot longer than I thought. I mean, I knew it was long, but... if not, we shall continue next time. Don't worry, I'll be back. Eventually. Speaking of which, this is actually my last stream before my hiatus. Okay, I'm ready. I'm ready to start again. Where did my pen go? Okay, there we are. So basically, anti-parallel means it's the other direction. Yes, it is equal, but it's just in the other direction. The parallel means that it has the same direction. It doesn't necessarily mean like it has the same magnitude, I guess. These are also anti-parallel to each other. They're going towards. So they still have like a 180 difference in terms of where they're going. And for number or number D, letter D. These have the same... Oh, I see. So these are equal to each other, even though they're like they have the same direction, and the length between the arrow and the line of the arrow is the same. So same direction because they're along the same path, and then they have the same magnitude. Orthogonal basically just means that it is perpendicular, so it creates this right angle. It can be perpendicular like that way as well. So it just means that the directions are perpendicular. I see that the length, the magnitude of this A is much shorter than B. So I guess orthogonal is only referring to the direction. So the ones that only refer to directions are A, which is parallel, E, which is orthogonal, and the rest of them have to all have equal magnitudes. So anti-parallels need to have the same magnitudes, and of course if it's equal it has to have the same magnitude as well. And yeah, parallel has the same direction, so does being equal to it, and anti-parallel is basically the complete opposite direction, just like a 180. I feel like this picture can explain it so much better than what I just said, but hopefully it helped a little. But we shall continue. Various relations between that. Okay, yeah, so that's just what I explained. Oh wait, it tells me. Okay, various relations between two vectors A and B. So A and B are not equal because the magnitudes, so that's part A, is not equal to each other. Vector A and B because they are not parallel and they don't have the same magnitude. Oh, they don't have the same magnitude. Yeah, I just realized that B is smaller. But vector A is not equal to the negative A vector because they have different directions, even though they do have the same magnitude. A and B is equal because they are parallel and have identical magnitudes. And then A is not equal to B because they have different directions. They're not parallel. And here their directions differ by 90, meaning they are orthogonal. Yes, the 90 degrees or the right angle is very important for when it comes to them sort of like intersecting to be called orthogonal. They has to be parallel. Okay. Check our understanding. Two motorboats named Alice and Bob are moving on a lake. Given the information about their velocity vectors in each of the following situations, indicate whether their velocity vectors are equal or otherwise. So we should see if their velocity vectors are equal or otherwise. Alice moves 6 knots north at 6 knots and west. Bob moves west at 6 knots. So no, these vectors are not equal because they move in different directions. So one is moving north and one is moving west. Alice moves west at 6 knots and Bob moves west at 3 knots. They're not equal because they have different magnitudes, 3 and 6. Alice moves northeast at 6 knots and Bob moves south at 3 knots. So once again, they are not equal because this time both their magnitudes and directions are not the same. Alice moves northeast at 6 knots and Bob moves southwest at 6 knots. So this is anti-parallel. They're anti-parallel, but they're still not equal to each other because they're going in like opposite directions. So the directions are not equal, even if the magnitudes are equal. Alice moves northeast at 2 knots and Bob moves closer to the shore at 2 knots. So yes, these vectors are equal to each other. They both move at northeast at 2 knots, even if they're like in different areas. So let's say this is Bob, he's near the shore, and this is Alice. And they're still moving in equal amounts and in the same direction. Okay, algebra of vectors in one direction. Whoa, are we ready to do some math? Or something like math? Let's create a little section for that. I feel like this could be almost its own section, but it's not. So it should be like right here. So algebra. I think I'm writing that too close to the picture. Of vectors in one direction, or one dimension. Vectors can be multiplied by scalars, added to other vectors, and subtracted from other vectors. We can illustrate these vector concepts using an example of a fishing trip scene in this figure. So, this figure, displacement of vectors for a fishing trip, stopping to rest at a point while walking from camp to pond. Go back for the tackle box at point D. Oh, okay. So these are like different examples. So just go this way to the pond. Suppose your friend departs from the campsite, which is point A, and walks in the direction to point E, the fishing pond, but along the way stops to rest at some point C located 3/4 of the distance between A and B. Beginning from point A, what is his displacement vector DAC when he reaches point C? We know that if he walks all the way to B, his displacement vector is relative to A, so DAB, which has a magnitude of 6 kilometers, and the direction of northeast. If he only walks 0.75 fraction of the distance, maintaining the northeasterly direction at point C, he must be at this operation, so 0.75 times that magnitude is equal to 44.5 kilometers away from the site at A. So his displacement vector at the rest of point C has a magnitude DAC is equal to 4.5 kilometers and 0.75 DAB, and is parallel to the displacement vector DAB because they're going in the same direction. All of this can be stated sequentially in the form of the vector equation. In a vector equation, both sides of the equations are vectors. The previous equation is an example of a vector multiplied by a positive scalar number alpha equals to 0.75. The result, DAC, of such a multiplication is a new vector with a direction parallel to the direction of the original vector. In general, when a vector is multiplied by a positive scalar, the result is a new vector that is parallel to A. Okay, so basically you can find the value, or I should say, you can find a different vector based off the vector you already have just using multiplication. So if you go to the exact same direction, you can just multiply, or you can basically just change that magnitude value to fit that new vector that you want. But we will write this as well. I think this is important. When a vector A is multiplied by a positive scalar value, it results in a new vector. So we have vector A. I'll write it like that. Multiplied. I'm a shorthand multiply as multi, and I'll put like a P. Multiply. I'm gonna just write it like that for short. A positive scalar alpha. The resulting is parallel. New vector, and I'll put b, or put new vector. Ah, no. New vector b is parallel to a. I'm gonna use like these lines as a representation of parallel. To A. There we go. And then let's write that equation. This example that we went over is important for when you want to find, I guess, in this case, because it's displacement, you want to find a distance of something. We'll put like A here. Hopefully I definitely left too much space. Oops. There we go. The magnitude of b, let's move on. The magnitude of b of this new vector is obtained by multiplying the magnitude of a of the original vector as expressed in the scalar equation. So we can get I'm gonna put a semicolon since this equation is technically related to this equation, just so it's like all in one line. We have b is that scalar value and a. In a scalar equation, both sides of the equations are numbers. So right, for this one, because it's a magnitude. The equation 2.2, which is this one, is a scalar equation because the magnitudes of the vectors are scalar quantities and positive numbers. If a scalar alpha is negative in the vector equation 2.1, then the magnitude b of a new vector is still given by equation 2. So I guess it doesn't matter if this is positive or negative. When it comes to magnitude, even if it is negative in here, it will not affect the magnitude value. I think the negative should only affect the direction. Then, yeah. Okay, oh yes, but the direction of the new vector is anti-parallel to the direction of A. Yes. So, I was right. These principles are illustrated in this figure down here by two examples where the length of vector A is 1.5 when a scalar value is equal to 2. The new vector is b is equal to 2a and has the length b is equal to 2a and equal to 3 units. Is parallel to the original vector. When the scalar value is negative, the new vector c is negative 2a and has a length c is equal to the absolute value of 2. So you still get the magnitude will not be negative still. Twice as long as the original vector and is anti-parallel to the vector. So maybe we should make an example for this one. I like how they explained it. So we'll write example. Or maybe it's I think I won't make an example of this. Instead, I'll just write down that if scalar is minus changes direction. Because Because I feel like this example has a lot more to go on, and then maybe we'll come back to it at the end, and then write out the example. Is negative, then change in direction, or opposite direction. Then I should say anti-parallel. I think anti-parallel is better. Parallel. Right? Yes, I think so. Yeah, okay, because if it's negative, it switches around 180. Yeah. Okay, I shall continue. Now suppose your fishing buddy departs from point A, the campsite, walking in the direction to point B, the fishing hole. But he realizes he lost his tackle box when he stopped to rest at point C, located 3/4 of the distance between A and B from the point A. So he turns back and retraces his steps in the direction towards the campsite and finds the box laying on the path at some point D, only 12 kilometers away from point C. What is his displacement, vector dA? Vector dAd, where he finds the box at point D. What is his displacement vector, vector dB? Vector dB from point D to the hole. We have already discussed that at the rest point C, his displacement vector is 1/4 of the original one, or the direction or the displacement of the pond versus the campsite. Starting at point C, he walks southwest towards the campsite, which means his new displacement vector is that from point C to point D is anti-parallel to AB. Its magnitude is 0.2, the original one, so 1.2 kilometers. So his second displacement vector is that. I think it might be easier for just me to like point at it than actually read out all the letters, because I think me reading out the letters is going to confuse me, and I will probably say the wrong letters and might confuse you as well. His displacement, that relative to the campsite, is the vector sum to the two displacement vectors, vector that from the campsite to the rest, and vector that from the point to point where he finds his box. So I think this one. So he goes to this one, has to find his box somewhere, so he goes like the other way, right? And he goes back. And then you kind of get this equation at the end. So he turns back and retraces his steps. Okay. I will erase this, but just for the sake of me understanding. So he goes to here. This is point C. Then he's like, I lost my tackle box. Then he turns around. Goes back. So that is point D. And finds the box. And then he goes again. So what is his displacement? So they want to find the displacement of this area from like the campsite. Let's just say that that's the campsite. Okay, I get it. Yeah, okay. And then you kind of just add the two because one of them is negative, or in the negative direction. And the other one's positive. Okay, that makes sense. So the vector sum of two or more vectors is called a resultant vector, or for short, the resultant. When the vectors on the right-hand side of the equation are known, we can find the resultant as follows. So we know what A and D is because we know what A, C, D is. We plug that in here, so we get this. And then we know that he went backwards like 0.2 of the way, so we plug that in, and then we get this. And then when your friend finally reaches the pond at B, his displacement vector, that from point A, is the vector sum of his displacement, so that AD from point A to D, and his displacement vector, this, from point D to the fishing hole, is equal to that. This means his displacement vector, this has the difference of two vectors. Difference of two vectors. Oh yes, okay. It's because the reason why there's a difference between the two is because it was not like one stop. So now that we know what A and D is, which is like from this way to that way, and then A and B, which is all the way, we can find like this area, which is the from D to B point. I'm sorry if this is not making any sense. I'm genuinely like partly relearning this myself, so it's a bit confusing for me as well. If you're a bit lost, no worries. I am too. That's why I keep going back. But I hope it's okay. I hope someone can learn something. That's really all I want. Second is anti-parallel because it's going in the other direction. Yes. So the thing is, if you want to switch these directions, then you just put a negative. Switch them by 180. Okay, equation. We obtained the second displacement vector by this. You know what A and B is. And you know that AD is this. Or this much of AB. So you can plug that all in. This result means your friend walked dB, which is equal to 0.45 dAB, and it's equal to 2.7 kilometers from the point where he finds his tackle box to the fishing hole. When vectors A and B lie along a line that is in one direction, such as the camping example, their resultant, this, and their difference, that, both lie along the same direction. We can illustrate the addition or subtraction of vectors by drawing corresponding vectors to scale in one dimension as shown in figure 2.7. So right here. Okay, so this is what this is explaining. Figure 2.7. The magnitude of this resultant is the sum of their magnitudes. So R, the resultant, is A plus B. Speaking of resultant, I should write that down. So I can write down a resultant vector is the sum of two or more vectors. Resultant vector / resultant. It's good, I understand most of it. Okay. Good to know, and thank you for confirming that. Two or more vectors. Yes. Where was I? Right here. The magnitude of the resultant can be summed like this. The direction of the resultant is parallel in both vectors. When vector A is antiparallel to B, we draw them along one line in the either head-to-head fashion or tail-to-tail fashion. So part C. Oh, like this. So to draw them anti-parallel, you draw them like that. The direction of the resultant is parallel in both vectors. The magnitude of the vector difference, that is the absolute value. So d is equal to the magnitude of the vector difference. Yes, because you take the magnitudes of a and b and subtract them of the difference of their magnitudes. The direction of the difference vector is parallel to the direction of the longer vector. In general, one dimension as well as higher dimensions such as the plane or in space can add any number of vectors, and we can do so in any order because the addition of vectors is commutative and associative, and multiplication by scalar is distributive. So here are like the properties of a vector and how to do math with them. But I do first want to take this and explain this. So we can, I guess A is showing us that we can multiply it by a scalar, and that will indeed tell us the magnitude. And if the scalar is negative, it is going to the opposite direction, or it will flip to the opposite direction. B, when you add two vectors together, you get a resultant, and you can get a resultant which gives you a larger magnitude, but it has to be the same direction, I think. And then the subtraction is the same concept. You can subtract them, and they will be like anti-parallel to each other because you need to add that like negative, which will flip the direction. So then you end up getting this. I think this is a nice, good example. I'm gonna screenshot this and include it into the notes. Does that work? Yes. Oh no! How come I can't click on it anymore? Okay. And then we'll write like these properties. I think these properties are very important. Properties. So we have, I'm gonna write them all in purple except the last one because that one has scalar values. But since I'm referring to vectors in all of this, I'm just gonna write it all in purple. Well, I should name them first in blue. Properties. We'll have associative. And distributive. Since these are all vectors, I'm gonna write them in purple. I wish there was an easy way where I could just change my color, like a hotkey. Maybe there is, or there can be. But I don't know that hotkey. Oh. No! Let's see. Will it fit? I think it will. In my notes. If not, I'll move it over. Oh, I forgot the parentheses. Plus C. Yeah, okay. And then distributive, got A plus A is equal to that. And you got A over here. So for me, this sort of feels like a more complicated version of just like addition, subtraction, and multiplication, because you do have to take account that there is direction. I remember learning this, thinking it was a bit difficult until I sort of realized, hey, it's the same thing. I just need to make sure I have all my negative signs correctly, and I don't... Why can't I draw that? I can't... Okay, and I don't, like, multiply something I'm not supposed to. What else? When adding many vectors in one dimension, it is convenient to use the concept of a unit vector. A unit vector, which is denoted by a letter symbol with a hat, such as U hat, has a magnitude of 1 and does not have any physical unit, so that the absolute value of U hat is equal to 1. The only role of unit vectors is to specify direction. For example, instead of saying vector that has a magnitude of 6.6 kilometers in a direction of northeast, we can introduce the unit vector U hat that points to the northeast. So say sequentially that vector DAB is equal to 6 kilometers and then U hat. Then the southeasterly direction is simply given by the vector negative U hat. This way, the displacement of 6 kilometers is southeasterly direction. This way, the displacement of 6 kilometers in the southeasterly direction is expressed by the vector. So, a unit vector can basically describe that direction, and it doesn't really have a physical unit, right? And when adding many vectors in one dimension, it's convenient to use the concept of a unit vector. The unit vector is denoted by a center of the hat. Only role is to specify direction. Yes, so this is important. Take that. Okay, so, oops. Unit vector. And it looks like, it's got a little hat on it, but it is bold, so I'm gonna make that purple. Put like U and then a little hat on top. Oops. Now, stop making random marks. And it's used to specify direction, but it is unitless. Direction used to specify direction, but unitless. Is my handwriting getting worse? I think it is. Maybe I'll zoom in. There you go, it's a bit neater. Yes, but there just has no physical unit. Okay. So basically, I guess you can assign this U hat with a specific direction, and then that direction can describe your vector as a whole. Okay, there's a ladybug walker. I'm gonna turn back my music. I really don't like that this playlist just shuts off. And it's like, oh, it's been 30 minutes. Are you still there? I'm like, yes, I put it on loop for a reason. Okay. Let's see. Much more. Okay, I'm determined to finish this section, but I do think after I finish this section, that will be it. I'm starting to lose my voice. And my brain cells are all used up. There aren't very many left. To be fair, there's not many. There weren't very many to begin with. So, the ladybug walker. This one I can't have in green because it's an actual example. A long measuring stick rests against the wall in a physics laboratory with its 200 centimeter end at the floor. A ladybug lands on the 100 centimeter mark and crawls randomly along the stick. It first walks 15 centimeters towards the floor, then walks 56 centimeters towards the wall, then walks 3 centimeters towards the floor again. Then after a brief stop, it continues for 25 centimeters towards the floor. Then again, it crawls up 19 centimeters towards the wall before coming to a complete rest. Find the vector of its total displacement and its final resting position on the stick. If we choose the direction along the stick towards the floor as U, then direction towards... Wait. If we choose the direction along the stick towards the floor as the direction unit, U hat, then the direction towards the floor is U hat plus. Oh, yes. And the direction towards the wall is minus U hat. Okay, 5 displacements. So what they're doing here is sort of breaking down this word problem. Where'd my pen? Here we are. So, and then they're defining the unit vector. So they define it as... That is quite terrible. Okay, wait, I was supposed to make it purple. Hold on. And I don't like that color either. I don't think I chose that one. I think I chose this green one. A lady bug walker so we have positive U, that one as defined as towards floor. So we'll put to floor, which in turn means the negative version, or the opposite version, is towards the wall. And there are 5 total displacements. So we can write it just like them. 15 centimeters towards the floor. So we'll write it like this. I don't know if they're going to change units. I hope they not, because I'm just going to write it as 15 and I'm not going to put centimeters. And then I'll put that towards the floor, then that, so that's 56 centimeters towards the wall, and that would be the negative U hat. 3 centimeters towards the floor again, so we have our third equation, or our third vector, I guess it's not really equation, or third vector description. Third, 3 centimeters towards the floor, stops, then continues, 25 centimeters towards the floor again. So it keeps going up, so that means it's still positive. So we got the 4th one. T5. We got, and it crawls up 19 centimeters towards the wall. So to the wall is the negative direction. Maybe we should like put parentheses around the negative ones, so at least you'll know. Okay, basically, yeah, then we do get these values. And here they have a lovely picture showing the displacement. So walks to the floor for 15 centimeters, so that's the first one. Walks towards the wall for 56, so that's part B. Or D2. Then we got D3, which goes towards the floor. It goes towards the floor again for 25. So 3 and 25, and it goes back up 19. And then we can like basically add them all together to get this resultant. And then I'll write that down. Well, it's all gonna be in purple because they're all vectors. Maybe next time I stream or continue this lesson, I'll find a different way to denote the vectors. Maybe I'll just leave the arrow on top and not bother with the colors. I mean, I will say, like, oh, this is a vector, this is not a vector verbally, but I don't know if the color thing, I don't know if I like that color thing I'm doing right now. It's not the best. So another way that they did this was, so they took all the values and like, if it had a negative u value, so the negative unit, what was this called? The unit vector. A negative unit vector would mean subtraction. And they just kept it normal, so it would be 15 minus 56 plus 3 plus 25 minus 19. So this is how I normally do it. They write it like the second line right here. Oh, you can't see. Can you see my... Okay, this right here. I don't really like doing that because actually this confuses personally me more than just me writing it like this. I don't know why. It's just when I look at it like this, it just seems so complicated and like convoluted and stuff. So if I just add if I basically just take the magnitude and then keep remembering which one has the negative and positive direction, that really helps me a lot when solving vectors versus like actually writing it out all like this. But I know some people work differently. But yeah, for me, that's my tip. I know that keeping that second line in will be helpful to a lot of people, and maybe they don't like it that way, or maybe they don't like the way I do it, but it's something to try if you find yourself being confused by this many things. Like there's so much stuff on the paper, if that makes sense. And then we'll stick it in your calculator and get the negative 32 cm. That's centimeters, and then you got that to the wall. So from the floor, it is up basically 32 centimeters. Yeah, so basically the ladybug will end up here. And since our unit vector is positive in this case, and we have a negative direction, so if the positive one is going down, and it's negative, that means we go up. So we go up 32 centimeters. So the ladybug will be right here. Check your understanding. A cave diver enters a long underwater tunnel. When her displacement with respect to the entry point is 20 meters, she accidentally drops her camera. But she doesn't notice it missing until she is some 6 meters far into the tunnel. She swims back 10 meters, but cannot find the camera, so she decides to end the dive. How far from the entry point is she? Taking the positive direction out of the tunnel, what is her displacement vector relative to entry point? Okay, so her displacement with respect to the entry point is 20 meters. Let's draw this out in green because this is technically an example. So we got let's call it cave example. I don't know what to call it. I'll just call it that. So we got the entry point. I'll have like the entry point right here. I'll just name it E for entry. Her displacement to the entry point is 20 meters. She's out like right here. Some sort of 20 meters. 20 meters. She accidentally drops her camera, doesn't know, but she doesn't know it's missing until she's gone some 6 meters far into the tunnel. So she goes another like 6 meters. 6 meters into the tunnel. She swims back 10 meters, but cannot find the camera, and she just like leaves. So she goes back, same direction. 10 meters. Please do not, these are not to scale. Okay, how far was she from the entry point? Is she taking the positive direction out of the tunnel? Taking the positive direction. What does that mean? Positive direction. What is her displacement? Vector relative to the entry point. Oh, I see. So here are to the entry point is u positive. I think that's what they're trying to say. So entry point would be 2e. And then we'll say negative. Is that what they mean by taking positive direction out of the tunnel? To tunnel. I guess. I think so. I don't know. So when she goes back, so it would be negative 20 minus 6 plus 10, right? And we'll add that. So we have negative 26 plus 10, so it'll be negative 16. 16 meters. And then we'll have that. So she's negative 16 meters out when she decides to go back. Yeah, okay. I think that's what they're looking for. I hope that's what they're looking for. I don't know because I don't have the answers. Does this look right? Does anyone think that this looks wrong or correct? But we just have a few more pages. 2, 3 more pages. Yeah. Is this Florida? I saw it, I was like, this must be Florida. Anyways. Man, I'm really losing my voice. It's okay. We shall continue. 2 dimensions. We finished the first 1 dimension one. Now we can do the 2-dimension one. Me, like, zoom out. I'm definitely super crooked. Well, it's actually not that bad. It's not that crooked. I think I did fix it a little. But anyway. Oh, did I do my math right too? Wait, 20? 20... Yeah, okay, I think this is right. I'm sorry if this is not. But, you know, maybe go check after the stream. I'm pretty sure this should be an answer online or something similar online. Probably right. Maybe I'm barely passing physics, so I'm not qualified to grade. No worries. I think that's what they're asking. What the part that confuses me is I'm not really sure what they mean by this, like taking the positive direction out of the tunnel. But Yeah. Okay. In 2D. Algebra in 2D. When lectors of vi. I can't read. When vectors lie in a plane, that is, when they are in 2 dimensions, they can be multiplied by scalars, added to either vectors, or subtracted from other vectors in accordance with the general laws expressed by equation those, so like the equations above. Basically these, and then these. However, the addition rule for 2 vectors in a plane becomes more complicated than the rule for vector addition in 1 dimension. We have to use the laws of geometry to construct resultant vectors, followed by trigonometry to find vector magnitudes, and directions. This geometric approach is commonly used in navigation. In this section, we will need to have at hand 2 rulers, a triangle, a protractor, a pencil, and an eraser for drawing vectors to scale by geometric constructions. Oh, I remember some of this. I really struggled with this part when I was learning physics, so we'll see how much I struggle again. It's been a really long time since I last learned. For a geometric construction of the sum of 2 vectors in a plane, we follow the parallelogram rule. Suppose 2 vectors A and B are at the arbitrary positions shown in figure 10 to 10. It's right here, A and B. Translate either one of them in parallel to the beginning of the other vector, so that after the translation, both vectors have their origins at the same point. Now, at the end of vector A, we draw a parallel line to vector. At the end of vector A, we draw a parallel line to vector B, and at the end of vector B, we draw a parallel line to vector A. The dashed lines in this. Okay. From the origin of the 2 vectors, we draw a diagonal that is a resultant R of the 2 vectors. The other diagonal of this parallelogram is the vector difference between 2 vectors D is equal to A minus B, as shown in figure 2AB. Notice that the end of the vector is placed at the end of vector A. So that was a lot. Let's see. So we have A. And what they did was they drew like sort of a line in between, and that is the addition. But then you have to remember that the magnitude of A and B is not equal to the magnitude of the resultant. Oh, wait, I see. Okay. I get it. So what they did was they took these 2 vectors, because they're like so far apart and not really connected. They decided to translate the A and sort of like connect it to B, and then from that you can draw a the resultant that kind of goes like in between both. I remember this now. Yes, and then here are like the parallel lines. Okay, so that's the steps. Translate one of them in parallel to the beginning of the other vector, so that they share their origins. Now that they have the same origin point, at the end of vector A, we draw a parallel line to vector b, and at the end of vector b, we draw another parallel line. Okay, I see. I think this would be great in a video. So what they did was they took like, it's kind of like this, right? Got A and B. But because they want these vectors to share the same origin, they essentially took A and like brought it down here. So it becomes like this. That's B now. And then A is like still like that. Okay, this is not really very, very much not to scale. I should at least try to make B longer than A. So it's like that. So that's A, B. Then they drew lines parallel to A, so they get this parallelogram, so that's why it's called that. And then you draw a parallel line from A that is, you draw a line from the point, the head point of A that is parallel to B, so it looks like this. And then from that you can get the resultant. Yeah, okay. Does that make sense? Does my explanation work? I hope it does. But yeah, so that's your resultant. Basically, you're adding that needs an arrow on top. But you're adding A and B, and the way to do it is to move around the vectors so that you can use this parallelogram rule to create the resultant and then find that this as the resultant vector. But you have to note that the magnitude of A plus B is not equal to the magnitude of the resultant. Yes, yes. This is actually kind of hard to explain in like words. I feel like a video format of this would just be so much more easy to understand, or much easier to understand. And then this one is the difference. So similarly, they translated the A and B to be in that like same direction. Okay, I see what they did. So this is for like addition. I should write addition. And then for the difference, or like subtraction, for subtraction, we have shorter A. And then we got B, or negative B, but we want to subtract that. Why don't they just write B? That makes no sense to me. But basically, you do the same thing. I'm not gonna write it as negative B because I don't like how they did that. They like flipped it for you, but I don't like how it's flipped. I want it to just be B. But I'll explain it. So we have like the same thing as earlier. You can translate it to so that they have the same origin point. We have A, got like A right here. Same thing as earlier. And then you draw the parallel lines, so just like earlier as well. The only difference is that instead of drawing like a line that goes here, you know, like across, you want to draw one that is from the top of this and this. So this, complete the triangle. This triangle, or this vector that you use to complete this sort of triangle shape, is your difference. Yeah, okay. I don't like how they made this B subtracted, or like minus B. I don't know why. That's just me. It follows the parallelogram rule that neither the magnitude of the resultant vector nor the magnitude of the difference vector can be expressed as a simple sum or difference of magnitudes A and B, because the length of the diagonal cannot be expressed as a simple sum of sides length. When using a geometric construction to find magnitudes, r and d, we have to use trigonometry rules for triangles, which may lead to complicated algebra. There are two ways to circumvent this algebraic complexity. One way is to use the method of components, which we examine in the next section. The other way is to draw out the vectors to scale, as is done in navigation, and read approximate vector lengths and angle directions from the graph. In this section, we examine the second approach. Okay. If we need to add 3 or more vectors, we repeat the parallelogram rule for the pairs of vectors until we find the resultant of all the resultants. For 3 vectors, for example, we first find the resultant of vector 1 and vector 2, and then we find the resultant of this resultant and vector 3. So if you want to do it for multiple vectors, you have to do it in steps. So you can't do like 3 at one time. You have to do 1 and 2, and then you take that resultant and then do number 3, and then you take that resultant and do number 4. The order in which we select the pairs of vectors does not matter because the operation of vector addition is commutative and associative, right, as we done before. Before we state a general rule that follows the repetitive applications of the parallelogram rule, let's look at the following example. So it is Florida. Florida scares me. Suppose you plan a vacation trip in Florida. Departing from Tallahassee, the state capital, you plan to visit your Uncle Joe in Jacksonville, see your cousin Vinny in Daytona Beach, stop for a little fun in Orlando, see a circus performance in Tampa, and visit the University of Florida in Gainesville. Your route may be represented by 5 displacement vectors, so we got A, B, C, D, and E, which is, I'm assuming these, A, B, yep, Tallahassee, Jacksonville, Daytona, Orlando, Tampa, Gainesville, and then I guess the resultant, which are indicated in red vectors. What is your total displacement when you reach Gainesville? The total displacement is the vector sum of all 5 displacement vectors, which may be by using the parallelogram rule 4 times. Alternatively, recall that displacement vector has its beginning at the initial position, Tallahassee, and its end in the final position, Gainesville. So the displacement vector can be drawn directly as an arrow connecting Tallahassee with Gainesville. When we use the parallelogram rule 5 times, the resultant R is exactly this green. Sorry, I can't read. When we use the parallelogram rule 4 times, the resultant R we obtain is exactly this green vector connecting Tallahassee and Gainesville. So you can use, I guess what they're saying is that you can use the parallelogram rule in steps all the time, but if you just know the beginning and the end, you can still draw a resultant vector from that. So you don't have to technically do it 4 times, but if you do, I think it's like the same, you do end up with the same vector or an equivalent vector. So from this, I guess we can write that we have to do vector addition in steps. So repeat parallelogram rule in steps. So you can't just do it all at the same time if you choose to go that route. That's not an H. In steps. Repeat parallelogram rule in steps, or if no start, or I should say origin, if you know the or initial position, if you know the initial position and the end position, initial position and end position, that should be your resultant vector as well. Resultant, use T-A-N-T, resultant vector, from point to point. Yep, okay, I think that makes sense, hopefully. So instead of doing like parallelogram rule a bunch of times, you can just say, well, I went here, 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 but then my resultant vector, I'm still like this much far away from where I started, and you just draw a resultant there. Drawing the resultant vector of many vectors can be generalized using the following tail-to-head geometric construction. Suppose we want to draw the resultant vector of 4 vectors. We select any of the vectors as the first vector and make a parallel transition of a second vector to a position where the origin tail of the second vector coincides with the head of the first vector. Then we select a third vector and make a parallel transition to the third vector to a position where the origin of the third vector coincides with the second vector. We repeat this procedure until all vectors are in a head-to-tail arrangement like shown in figure this one. We draw the resultant vector by connecting the origin tail of the first vector with the head, the end of the last vector. The end result vector is that the end of the last vector. What? The end result of the end of the resultant vector, is the end of the last vector. Because the addition of vectors is associative and commutative, we obtain the same resultant vector regardless of which vector we choose to be first, second, third, or fourth in this construction. Okay, so for this, if you have a bunch, you can basically move them wherever you'd like. So I think they started with vector D, it's right here. Then they wanted to go to A, it's right here. So the tail to head, then we connect the other vector A from the head to tail thing, so we get the tail of A, and then we connect the head of A to tail of C, and then do the same for B, and then we can get this long line that is the resultant. So from this, we know that we can use tail to head geometric construction, tail to head. Why is that hard to say? That almost feels like a tongue twister. It's not, and it shouldn't be. Hello! Thank you for following, Chubby Puppy. Oh, your name is so cute! I appreciate it. Ah, where did my stuff go? Tail to head, geometric construction. I love bears. Sorry, I said that because of your username. That was not a random thought. Well, I guess it kind of was. Tail to head geometric construction. So you connect the tail of one vector to another, or just like, maybe I should just say connect vectors together. yes, connect vectors together. And you can draw resultant from tail of first vector to head of last vector. Of first vector to tail of last. Or to head of last vector, sorry. Head of last vector. Okay. Use an example. I guess this will be our last example for today. And my voice is absolutely destroyed. I wonder how people can like talk for like 6 hours straight. Like, do you not get tired? I find that genuinely impressive. But next time we shall... Oh. Next time we shall continue. This will be our example. So geometric. Construction. Okay, geometric construction of the resultant. 3 displacement vectors, A, B, and C. Figure this one are specified by their magnitudes. A is 10, B is 7, C is 8, respectively by their respective direction angles with the horizontal direction. Oh, there's angles. Okay. Yes. I don't know, for some reason, because I saw them denote like a scalar value with the alpha a lot. I was like, what? I thought they weren't supposed... Can you have that? Like, are you allowed to have an angle that as a scalar? Whatever. Anyways, I was a bit confused, but no, they're just referring to the angle of the vector, basically which direction it's pointing to. So we have 35, negative 130. The physical units of the magnitude are centimeters. Okay. Choose a convenient scale. I have to get a protractor and a ruler. I don't have a protractor. I don't know if I have a ruler either. Well, it'll be fine. I'll still read through the solution. Choose a convenient scale and use a ruler and protractor to find the following vector sums. So A and B, and D is equal to A minus B, and C is equal to this. So let's think about this for a little bit before I continue. So with A and B, I could do the head to tail method, but usually that one is more preferred for ones with like many vectors. I could just do the parallelogram method, which I would just draw the A like this, or I could just like translate it to here, you know, and then there would be a line in between both. For D and A, I feel like the first two you should do the parallelogram method, and for the last one, what is F? Hold on. Why is there an F? Okay, well, for the last one, I think using the tail to head might be more useful. Maybe. But then how would I subtract that? We'll see what they say. Okay, strategy. In geometric construction, to find a vector means what? To find a vector means to find its magnitude and its direction in angle with the horizontal direction. The strategy is to draw a scale is to draw to scale the vectors that appear on the right-hand side of the equation and construct the resultant vector. Then use a ruler and protractor to read the magnitude of the resultant. So I literally cannot do this right now, but that's fine. And the direction angle. For parts A and B, use the parallel... Oh, it even tells you! Wow, I was looking up here thinking like, what should we do? And it just tells you. But I mean, it's good to think about it, right? For C, we use the tail to head method. Tip the tail and parallelogram are the same. Parallelogram is just tip the tail of A and B plus B. Yeah, I know that they're like, you can get the same thing from it. It's just like visualizing what you have to do. I find that if you only have two vectors that you need to deal with, the parallelogram like is more intuitive to me than the tail to head or tail to tip method. But when there's multiple of the vectors, it's more intuitive to me to do the tail to head. Although you're right that they should both work. I spent time thinking about it, and it just gave me the answer. For parts A and B, we attach the origin of vector B to the origin of vector A, as shown in that. Yep. And construct a parallelogram. The shorter diagonal of this parallelogram is the sum A and B, and the longer of the diagonals is the difference. We use a ruler to measure the lengths of the diagonals and a protractor to find the angle. I will not be doing that, but I can still draw it out for fun. Why not? I know that they did it, and of course mine will not look nearly as nice. But I will draw like the dotted lines for the parallelogram method. So they basically translated this vector to like here so that they share the same origin. Kinda looks like this. Right? I think so. And then you want to draw lines that are... Oh, that's not parallel. It's supposed to be parallel. Like that. Ignore these ones. Just, you know, they were never there to begin with. So we'll have this. And then this... maybe I'll... This. So this is your resultant, so that will be your addition. Wow, this will be your result. Can I draw a line, please? There we go. That will be your resultant. That'll be your R. Is this linear algebra? Is it? I mean, technically, I guess? The very beginning of linear algebra? We're learning about vectors in the concept of physics. Well, that's the focus, I guess. Linear algebra has left my brain years ago, and quite frankly, I don't think it was even there. But we'll do this for the difference. For the difference, we can draw... Okay, stop. Like this. Hold on. When you do the difference... Okay, the -1 has... So I was drawing it the wrong way, but it should still be fine. Was I? Yes, okay, so I guess that clarifies it for me. It should be drawn this way. Because it's A minus B. Okay, that's a squiggly line. Please ignore. It should be a straight line. And this is how you know I don't have a ruler. Like, the bottom side is A and B, and the right side is A and B. Vector addition is Albanian. Yay! But yes, so this is how they did it. Oh, they did it out here too, but I think it was a nice drawing it. So they get this, and for this one, it was like right in between the two, so the angle did look like 0. I can't say that. I don't know how long this is because I don't have a ruler or a protractor, clearly. But yeah, and we shall do the third one, which is the tip to tail method. So. Okay, right, it's 3B. Maybe I should write this to not confuse myself as much. It should be equal to A minus B. And then we'll have the green one as the addition, which was the resultant, so R A plus B. Then we have I'm gonna use purple for this one. What was it? S. S is equal to A minus B plus C. Yeah, okay. So we can draw AB. B has to be super long. The funny thing about this... Okay, so they did flip B. That's what I was wondering. If it's negative, they have to flip the B, right? Originally, I was gonna do it as a... Well, okay, I'll do it the way I was gonna do it first, and then it should be the same thing, but I was just gonna draw A like this. Okay, maybe I'll go lower. That will be A. And then B is pointing this way, so it should be pointing like up this way a lot. And it's like 3B. And then C was gonna be even more up. I don't think that's right. I don't think I'm supposed to do it like that. But does that equal the same thing? Why does it look so funny? Negative 3B. Yeah, but regular B is pointing down, right? So if it were B, it would be like this. Right? But because it's negative, it flips the other way. So it does 180. And then goes like that. And then we got C, which is like this. Yeah. That looks right. Just don't look at my drawing. Oh, I should draw that one in purple. I should really... Oh. My pen fell off the tablet. Yeah, don't drop... Oh, right. Sorry, I didn't understand what you meant, but yes, I should not drop the sign. There we go. Yeah, that's right. No BS. Okay, I am correct. Why does it look so bad? Anyways. So what they did instead was they started with the B, had A and C. In addition, next we draw that from the origin. Okay. In vector addition, the order in which we draw the vectors is unimportant, so you can draw it whenever. But draw the vectors to scale is very important. Well, I didn't do that either. No. Oops. Next we draw the vector s from the origin of the first vector, which in my case was a, but in their case was b, to the last vector in place to the arrowhead at the end of s. We use a ruler. I did not use a ruler to measure the length and find its magnitude as that in centimeters. We used a protractor to find its angle, and it's that. Would be nice to get a ruler. I haven't touched a protractor in like so long. I don't think. Yeah, I never heard the word protractor in such a long time. Anyways. Oh, so that's why F was there. Shall we do the extra exercise? Using the 3 displacement vectors, A, B, and F, choose the convenient... Okay, I will not be doing that. But find the vector G given by this equation. So, why not? Since we're here... No, I don't... I dropped my pen. Hold on, give me a moment. Alright, I need to stop talking with my hands as much. I have a horrible habit of doing that, is like using my hands a lot. Maybe one day I'll get like a hand tracker. But then you'll be able to see that I fling my hands everywhere. Anyways. Let's continue. Such a bright red. I don't really like bright reds. I mean I do, but not when writing notes. It scares me. Makes me think I did something wrong. So let's use like darker red. Almost maroonish color. Alright, there we go. No! I caught it! I caught it this time. And then we'll have the vectors. So A, B, and F. But F should be negative, so it should go the other way. Let me move that up so you can see it better. So I'm gonna start with A this time. So we got like A. And then we have B that kind of goes down here, but it's like 2B, so it's a bit longer. And then F, which is negative, so we flip it the other way and it goes like this a little bit. Yeah. Am I doing this right? Does this look right? And then I simply take that and I draw the end result from here to here. That will be RG, I think. 2 down, and I flip the F so it points downwards, and it's because it's negative. I don't need to add any more on the F, do I? No. Okay. Yeah, I think this is right. So this is how your resulting G vector should look like. But yeah, that was actually the last example of today. Hopefully, you learned something, or like at least I was somewhat helpful for something. That's really honestly my only goal of like doing this on stream, and quite frankly, streaming, or one of my only goals on stream. My goals are to entertain as well as to encourage learning and, you know, stuff like that. But yeah, I hope that's right. Thank you all for coming, and this is my last stream before the hiatus. But before I leave, because I'll be leaving for like 2 months, like a month and a half, I think I'll be back in April, like April 17th or something, or April 21st. But yeah, thank you all for coming. I shall read the results of the poll. Wow, so everyone who has showed up today said that they've learned it sometime during at some point in their life. So it says, yes, I still remember. 56 of you. Well, you 56% of you, you're probably in a better place of learning these vectors than I am, because I completely forgot this. And the rest of you were the category which I am personally in. 44%, yes, but it's been a while. I forgot a lot of stuff, but it was really nice relearning this. And yeah, thank you for the stream. Gonna miss you. I'm gonna miss streaming, but I'll be back. I actually, this time I will be online. Usually, previously when I went on hiatuses, I would always have some sort of video backed up, but not this time. I just need to figure things out, but I'll be back eventually. Don't forget about me. But I'm gonna find someone to raid on Twitch, and hopefully we'll see someone. I know that there's just like there's this physics VTuber that I think that they're an actual like physics teacher too. I don't know if they're on, but let me check if they are. If you would like to raid with me on Twitch, feel free, and if not, that's totally fine too. I really appreciate you showing up and saying hello, or just even watching. So, yes. Thank you for coming to my last stream before I go on hiatus. When I'm back, I have huge things to announce and a lot of food to share. So they are not on. Let's see if this person looks new. Let me try to find. Are there no VTubers in this category? Okay, I guess there are no VTubers in this category. Dang, that makes me sad. I mean, of course I know that there are, but at least the ones that I know are not on. So, maybe I'll raid into someone playing a game. Oh, Bear's on! They're playing Elder Scrolls 5, which I've never seen before, but they're super nice. They're also a bear, or their username is Bear, and I like bears. I think I'm gonna raid them. But if you'd like to join, give them a warm welcome, and it would be much appreciated. But if not, absolutely no worries. Please take care of yourself. Keep on studying. I'll be back with, like, the other lessons. So we're gonna be raiding this person. Wait, let me wait for the raid message to show up. I like this music. Bye. Okay, in a few seconds. Why am I so bad at this? I wish YouTube had a smoother way to raid for someone who's smaller. You can raid on YouTube, but you have to be a specific number. But yeah, we're gonna raid this person. I'm not saying bye yet, hold on. Yeah, I really do appreciate all of you for joining, especially for my last stream. I know that physics can be intimidating, and quite frankly for me it very much was. But I appreciate the effort in trying to learn, and I hope you learned something, even if you didn't. Even if, like, maybe it's not your thing, but I hope there's at least some value in somewhere. But yeah, thank you all. Be ready in a few seconds. So 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Beep boop. Bye everyone. Bye bye. See you after hiatus.